And here's your momentum operator, your hat, P of x. Now, we found, in earlier lectures, we found the operator corresponding to momentum was minus IH bar dV dx. Okay. Now, if you're talking 3 dimensions, it would be minus IH bar del, the upside down triangle, pointing down, the del operator from vector calculus. But anyway, just here, keep it simple, just deal with 1 dimension. So minus IH bar dV dx. Okay, so that's your operator for momentum, x component of momentum. So now to use this formula, we need the commutator. So we need to, we'll let A be the A hat be the position operator, so x hat, and we'll let B hat be the momentum operator, so P hat. Okay, so we need to find the commutator. What's the answer to the commutator of A hat and B hat, or x hat and P hat? Okay. So here, this is what we need to find. Now, now these are operators. They operate on something. They change something. And what's the something? Well, the psi function, and your state vector, or whatever you want to call it, psi. Okay. Well, what is the commutator? So it'll be xp minus px. So now this is just a constant from your p. So you bring it to the left. So you'll have xp. In other words, x dV dx. That's xp, right? Psi. And minus px. Now, you got a minus here already, so minus minus gives you this plus, IH bar, P, that's the dx, Px psi, right? Px psi. Now, that's just high school calculus, so work it out, and things cancel, and you're just left with just IH bar psi. That's what things cancel down to. Now you've got a psi here and psi here, so that means the commutator is IH bar. Oh, I've forgotten to mention this. Yeah, that's important. Let me go back to that. Now you may be puzzled by this I here, and you may say, well, the left-hand side is just squared, so whatever this is, it's going to be positive, right? And you got a square here and the I here. So if you just square the I, you get minus something. So this should be greater than this trivially, right? Because this is positive and this will be negative. But there's a fault in the logic. These two operators here are Hermitian, and it works out that the commutator of 2 Hermitian operators gives you a result that contains an I, right? And the I coming from this commutator cancels with the I here. So therefore this inequality is not so trivial. Okay. So the bottom line was that the commutator here between A hat and B hat gives you something with a factor I, square root of minus 1, in it. And this one's I and that I cancel. So that's what I'm just saying here. And here's an actual example, you see, because the commutator here is I H bar, right? And that I will cancel with the 2I from your formula, general formula. Okay, so the commutator is I H bar, and therefore take this expression. This is now IH bar, okay, and the i's will cancel, so you'll get H bar over 2 squared, right? So you now these are just constants, so the expectation value, the average value of the constant is just the same, it's constant. Okay, so now this is sigma, right? It's the standard deviation. Now for the Heisenberg uncertainty principle, now we're using much more rigorous math. we defined the uncertainty, this delta x, as the standard deviation. So this delta x here and this sigma x, same thing by definition. Okay? So here's what we got from the general formula here. Okay. So the i's cancel, you get h bar squared over 4, so you get this. So this sigma x squared times sigma p squared, which is the standard deviation x times, in other words, the uncertainty x times the uncertainty p squared, is greater or equal to h bar squared over 4, take square root of both sides, and hence delta x delta p is greater or equal to h bar over 2. Now that's interesting. See, we've got a more exact estimate of what this right hand side is for the Heisenberg uncertainty principle. Before we were sort of saying roughly, larger or equal to h bar of some sort, but now we're more precise because we've done it mathematically, and we're defining the uncertainty now as the standard deviation. So we're using statistics to make this more precise. Right? So there's a concrete example of this more general formulation of the uncertainty principle, the Heisenberg uncertainty principle. And this formulation is usually called the generalized Heisenberg uncertainty principle. Right? And it's valid for any two observables that are incompatible, that you cannot measure both of them with infinite accuracy simultaneously. That's the definition of incompatible. All right. Now a bit of a discussion just to end up with. Imagine, now it's hypothetical, right? It's like if pigs had wings, but because as far as we know, I think I've mentioned this before, but in terms of laboratory experiments, science has gone down to a scale of about 10 to power minus 18 of a meter. What is that? It's a zeptometer? I think that's a zepto. Attos? Hold on, let me think. Femto's 10 to the minus 15. So it's an attometer, 10 to the minus 18 of a meter. And quantum mechanics seems to be working at those tiny scales. And since string theory seems very indirectly to be starting to be confirmed, the various phenomena that suggest string theory is on the right track, not solidly there yet. I mean, things will get a real boost if, hopefully soon, with the LHC, Large Hadron Collider, that it confirms the existence of supersymmetric particles, the symmetry between fermions and bosons. If you don't know what I'm talking about, don't worry, but if you follow me on particle physics courses in the future, you will. But so if supersymmetry is confirmed, then that came out of string theory. So string theory is confirmed, and string theory goes right down to 10 to minus power 35 of a meter. So, and that's as far as humanity knows about, even in terms of ideas. So it looks as though quantum mechanics is valid all the way down, right down to 10 to minus 35 of a meter. Now, if that's the case, then this idea of suggesting that h bar goes to 0 is very hypothetical. But if it does go to 0, then these uncertainties dry up, right? If h goes to nothing, then these can also become nothing. So there's no uncertainty. So you can measure the position and the momentum to infinite accuracy. Okay, so if h goes to nothing, this product here can also go to nothing. So then there's no incompatibility between observables, right? And therefore you get the classical case. Now that kind of thinking is an example of Bohr's, B-O-H-R, Niels Bohr, his correspondence principle, which in broad terms means that in certain limits, quantum mechanical limits, you should then approximate what's happening in classical mechanics. So in a sense, the limit of quantum becomes classical, in a sense. So yeah, so this kind of reasoning, you know, in the limit, in the quantum limit, when h bar Planck's constant goes to 0, then your uncertainty should disappear, and that's typical of classical mechanics. Doesn't have incompatibility of observables. You can measure anything infinitely accurately and simultaneously. That's classical thinking. Okay, now the Heisenberg uncertainty principle in quantum mechanics applies also if this is y and the y component of the momentum, you'll get something similar. Similarly for the z component at p of z, the z component of the momentum, right? So you'll get a Heisenberg uncertainty principle for this and for this. Now for all the other combinations of position components, you know, x, y, z, and momentum components, you know, px, py, pz, other than these three, you know, this one and this one and this one, any other pairs, the commutators equal 0. I don't know if you can see that here. This just says xi, the commutator of xi and pj, where I and j are different, then the commutator is 0. Okay, so you may be surprised. Like here's the position, here's the momentum, but this is the ith component. For example, it might be x, and this is the jth component of the momentum. It might be py or pz, right? But the commutator will be 0. Okay, so that's it for the generalized Heisenberg uncertainty principle. Very useful. Now the next session, we'll completely change topic. We'll talk about symmetries in your physical setup, and from those symmetries you can derive conservation laws. In other words, certain physical quantities do not change with time. So the dBdt, or whatever it is you're talking about, remains, well, it's 0, it doesn't change. And that's for next topic.